Hello everybody, welcome to Lecture 20. So our plan today is to complete our work on Chapter 3 about eigenvectors, similarity and diagonalizability. And yesterday last time we just left off with a discussion about determinants, and we had seen how to compute determinants in general using this sort of recursive approach by calculating the cofactors of the entries in any row or column. So we're going to pick up there today and look at an example of computing the characteristic equation or the characteristic polynomial of a 3x3 matrix by calculating a determinant. So just a few remarks, first of all, about the methods that we looked at for calculating determinants and about some properties of determinants in general. The first remark is the cofactor expansion method that we talked about is something that we used as the definition of the determinant. It also gives us a method of computing determinants, but I just want to make the comment that it's generally not the most efficient way to calculate determinants. So the method, once again, just to recall it, is we've got a square matrix. Its determinant is a number that depends on the entries in complicated ways, and the matrix is invertible if and only if its determinant is not zero. So the determinant is a number that you can compute from the entries of a matrix that tells you whether or not the matrix is invertible through the question of whether the determinant has the value zero or not, which is quite a neat thing in the sense that it's quite nice that such a number exists. But the difficulty with it is it's not very easy to compute and it's not very efficient to compute. So our definition of the determinant from yesterday was it's the number that you get if you take any row or column of the matrix. For each position in that row or column, calculate the corresponding cofactor. And what that is the following. The cofactor of the entry in position ij in the ith row and jth column is what you get if you delete row I and column j from the matrix. Calculate the determinant of the n-1 by n-1 matrix that remains, and possibly adjust that by changing its sign, depending on what the position in the matrix is, as we saw last time. So basically, this is saying that in order to calculate an n by n determinant, you need to be able to calculate n-1 by n-1 determinants. Okay, given that we can calculate 2 by 2 determinants, we can basically build that up to calculating 3 by 3 determinants, 4 by 4 determinants, 5 by 5 determinants, and so on. So that's what I mean by saying that it's a sort of recursive process in the definition. So what we're saying here is if we take any row or column of our matrix, calculate the cofactors of all entries in that row or column, there are n of them, and each one of them is an n-1 by n-1 determinant, multiply each entry by its own cofactor, add those numbers together, and what you've got is the determinant of the matrix that you started with. So that's a sort of probably not easy to follow description, but hopefully it makes sense in conjunction with the content of the last lecture. But the point is, to calculate a 5 by 5 determinant, for example, using this method, we need to calculate 5 4 by 4 determinants. Each of those involves the calculation of 4 3 by 3 determinants. Each of those involves calculating 3 2 by 2 determinants, and so on. So the amount of calculation to do to calculate an n by n determinant increases very rapidly as n increases, which is really the point of this first comment on this slide, that the cofactor expansion method is generally not the most efficient business if you actually want to use it to compute determinants. Okay, if you use it to define the meaning of a determinant is fine, but basically if we actually want to compute them, there are other ways to do it that are computationally more efficient and more reliable as well. And we're not going to get into that really in this course, but it's an observation for now. For 3 by 3s, the cofactor expansion method is good enough. It's certainly good enough for our purposes, and it's not particularly inefficient, but the efficiency of it decreases rapidly as the size of the matrix increases. That's the first observation. Okay, second remark is that if the matrix has some special sort of structure, for example, if it has a lot of zero entries, something like that, then the determinant can be easier to compute in principle and in practice. So for example, if the matrix A is upper triangular or lower triangular, then its determinant is just the product of the entries on its main diagonal. So upper triangular means that all entries above the main diagonal can be whatever you like, but the entries below the main diagonal are zeros, so that all the non-zero entries are contained on and above the main diagonal. Lower triangular is the transpose of that. A matrix is lower triangular if all of its non-zero entries are either on or below and to the left of its main diagonal. And of course, a diagonal matrix is both upper triangular and lower triangular, so it fits into this description as well. So if a matrix is upper or lower triangular, including if it's diagonal, then its determinant is just the product of the entries on its main diagonal from upper left down to lower right. Okay, that's one observation, and that actually follows from the cofactor expansion description. If you take the first column or the last row and do cofactor expansion by that choice, and look at what happens. You'll be able to deduce that statement. Okay, another thing that can arise, which is of interest sometimes, is that if you have a matrix, which is what they call a block triangular structure, which means that maybe it has a square block in the upper left, maybe of size k by k, and a square block in the lower right of size n minus k by n minus k, which can have whatever you like in them. But if the block in the lower left that's below the k by k square and to the left of the n minus k by n minus k square, so if there's a n minus k by k block in the lower left, which is full of zeros, then we say the matrix is block upper triangular. And in that case, its determinant is just the product of the determinant of the k by k block in the top left and the n minus k by n minus k block in the lower right. So it's just the product of those two smaller square determinants. And in particular, whatever is in the sort of upper right region doesn't really enter the picture of the determinant. So that's a property of determinants that's sort of worth bearing in mind, that if you have a block triangular matrix with square blocks along the diagonal, then its determinant is just the product of the determinants of those square blocks. Third property, which is an important one, is that if we have a pair of n by n matrices, A and B, then of course one can look at their product AB, and it again is a square n by n matrix of the same size. So a fact that is not at all obvious about determinants from the way we've defined them is that the determinant of the product of two matrices is just the product of their determinants. This is referred to as the multiplicative property of the determinant, or sometimes as the Cauchy-Binet formula. And it's something that's not obvious at all, but is extremely useful, very definitely worth bearing in mind. Not too hard to prove for 2 by 2 matrices, or even for 3 by 3s, it's manageable, but it's not easy to prove in general. But it is a remarkable property of determinants, which has uses all over the place. So definitely worth keeping in mind. We're not going to prove it in this course, although you'll certainly easily find proofs of it if you're looking for them. Okay, and a consequence of the multiplicative property of the determinant is that matrices that are similar to each other, which remember means A and B are similar, if A is equal to P inverse BP for some invertible matrix P. So similar matrices have the same determinant and the same characteristic polynomial. We already kind of knew that they have the same characteristic polynomial because they represent the same linear transformation with respect to different bases. They also have the same determinant. And we'll see why that is. We'll also look at a 3 by 3 example. Okay, so just to see why it follows from the multiplicative property of the determinant that similar matrices have the same determinant, let's just note that if we have a pair of matrices A and B is similar to A, then B has the form P inverse AP for some invertible matrix P. And using the multiplicative property of the determinant, we can observe that the determinant of P inverse AP is equal to the determinant of P inverse times the determinant of AP. These two are just numbers. They're entries, they're elements of our field. So this is equal to the determinant of AP times the determinant of P inverse, which is equal to the determinant, again, by the multiplicative property of the product AP P inverse. But P inverse is the identity matrix, so this is just equal to the determinant of A. So if B is a matrix which is similar to A, then the determinant of B will always be equal to the determinant of A. And similar reasoning tells us that the characteristic polynomial of B will be equal to the characteristic polynomial of A also. Okay, here's an example of a 3 by 3 matrix B, whose characteristic polynomial we would like to compute. So B is the matrix, here it is, with entries 5, 6, 2, 0, -1, -8, 1, 0, -2. So in order to calculate the characteristic polynomial of B, we have a 3 by 3 determinant calculation to carry out. Okay, so here's our matrix B. The characteristic polynomial of B is determinant of lambda times the 3 by 3 identity matrix minus B. And to write down that matrix, in each position, we've got lambda times the corresponding position of the identity matrix minus the entry in the same position of B. So in the top left, we've got lambda times 1 minus 5, 5 here in the top left of B. With the rest of row 1, we've got 0 minus 6, 0 minus 2. In row 2, we've got 0 minus 0. We've got lambda minus 1, so lambda plus 1, that position on the main diagonal. And we've got lambda plus 8 sorry, we've got just plus 8, 0 plus 8. Down in the lower left, we've got 0 minus 1, 0 minus 0, and 0 and lambda minus 2, so lambda plus 2. So the characteristic polynomial of this B is the determinant of that matrix. And to calculate this determinant, we have a choice of choosing a row or column with respect to which to compute the cofactors. One piece of advice generally when you're doing this is if you happen to have a row or column that contains some zeros in it, it's a good idea to choose such a row or column. So we could choose, for example, here, column 1. It's got a 0, which means we don't have to bother computing the cofactor of that entry because it's going to get multiplied by 0. So this determinant is using the first column, we've got lambda minus 5 times the determinant of the 2 by 2 matrix that remains when row 1 and column 1 are deleted. So that's lambda plus 1 times lambda plus 2 minus 0 times 8. We've got 0 times its cofactor, that part is 0, and then we've got plus minus 1 times its cofactor. When the first and third rows are deleted from this matrix, what remains is the determinant of this 2 by 2 matrix in the upper right area. So we've got minus 6 times 8 minus 2 times lambda plus 1. Okay, we carry out this calculation. We've got lambda minus 5. And here we've got a quadratic term, lambda squared plus 3 lambda plus 2. And then we've got minus, over here we've got minus 48 plus 2 lambda plus 2. So gathering everything together here, expanding out the cubic term on the left, we've got lambda cubed minus 5 lambda squared plus 3 lambda squared. Lambda cubed minus 2 lambda squared. We've got minus 15 lambda plus 2 lambda. So minus 13 lambda. We've got minus 10 as the constant term. And from that, we're subtracting, we've got minus 46. So minus 46 is plus 46. And we've got minus 2 lambda. So overall, our characteristic polynomial is lambda cubed minus 2 lambda squared minus 15 lambda minus 10 plus 46. Okay, so the eigenvalues of this matrix lambda are the roots of that cubic polynomial. And in general, of course, we don't really have an easy method for factorizing cubic polynomials. We can search for examples of integer roots. And if we do so, we might notice that 3 is a root of this polynomial. If we put 3 in here, we get 27 minus 2 times 9. That's 27 minus 18, so that's 9. Minus 45, that's minus 36, plus 36 is equal to 0. And that tells us that lambda minus 3 is a factor of this polynomial, and the corresponding factor has a lambda squared in it. It has minus 3 times something to give us 36, so minus 12. And then we can figure out that the missing term is plus lambda. So in fact, we find that our polynomial is equal, can factorize as lambda minus 3 times lambda minus 3 times lambda plus 4, which is lambda minus 3 squared, times lambda plus 4, and our conclusion is that the eigenvalues of B are lambda equals 3, which occurs twice as an eigenvalue, twice as a root of the characteristic polynomial, and lambda equal to minus 4, which occurs once. Okay, so the last thing that we're going to consider really is the significance of an eigenvalue occurring once or more than once as a root of a characteristic polynomial. So here's the example that we'll work with. Okay, so supposing that we want to calculate an eigenvalue, an eigenvector of the matrix B corresponding, for example, to the eigenvalue 3. We can certainly go about that task. So just a bit of terminology. So the eigenvalue 3 occurred twice as a root of the characteristic polynomial. There's the factorization. And so we say that it has algebraic multiplicity 2 as an eigenvalue of B. And we would say that the other eigenvalue, lambda equal to minus 4, has algebraic multiplicity 1 because the factor lambda plus 4 appears once as an eigenvalue, once in the characteristic polynomial. Okay, so the geometric multiplicity of each eigenvalue is the dimension of the corresponding eigenspace. So the dimension of the space, the geometric multiplicity of the eigenvalue 3 is the dimension of the space of vectors with the property that b multiplied by v is equal to 3 multiplied by v. So that's the dimension of the null space of the matrix 3 times the identity minus b. So here it is, 3 times identity minus b. So basically 3, 3, 3 on the main diagonal minus the entries of b in all positions. This is what it is. We expect it to have a non-trivial null space because we know that this matrix has determinant 0 because 3 is a root of the equation determinant of lambda identity minus b equal to 0. So if we take that matrix and reduce it to reduced row echelon form, here's the reduced row echelon form that we get. It's got 2 leading 1s in the first 2 positions, and that's telling us that the third variable is a free variable. There's one free variable, so basically we get a one-dimensional space of eigenvalues. If we give the name t to the value of the third variable in a solution space of the system, so a solution of the system is a vector for which 3 times identity minus b is equal to the 0 vector. If we name the variables x, y, z and say that t is the value of z, then the second row here tells us that y should be equal to minus 2t, and the first row tells us that x should be equal to 5t. So the null space of that matrix is a set of all vectors of the form 5t minus 2tt, all scalar multiples of the vector 5 minus 2, 1. So it's a one-dimensional space, and that tells us that 3 has geometric multiplicity 1 as an eigenvector of b, and it has algebraic multiplicity 2. If you calculate eigenvectors for the second eigenvalue minus 4, you'll find that it has geometric multiplicity 1 as well as having algebraic multiplicity 1. Okay, so the last thing that I want to mention in this chapter is this observation that the geometric multiplicity of any eigenvalue of any matrix can never exceed the algebraic multiplicity. And the reason for this can be deduced from thinking about the meaning of eigenvectors and the concept of diagonalizability. Okay, so we're going to suppose that some eigenvalue mu has geometric multiplicity k as an eigenvalue of a square matrix A. Okay, so that means that there is a k-dimensional eigenspace of A consisting of eigenvectors with eigenvalue mu. So there are k-independent vectors. We can call them v1 through vk with the property that A multiplied by any of these vectors is equal to the same vector multiplied by the scalar mu. And if that's true for v1 down to vk, it's also true for any linear combination of v1 down to vk. So they generate, they span an eigenspace of A. So we're going to assume that the eigenspace of A corresponding to the eigenvalue mu has dimension k and is given by, and has a basis consisting of the vectors v1 down to vk. And what we want to deduce is that mu must then occur at least k times as an eigenvalue of A, in the sense that the factor lambda minus mu occurs at least k times as a factor of the characteristic polynomial of A, so that the algebraic multiplicity of mu is at least equal to k. Okay, so here's our basis, v1 through vk, for the mu eigenspace of A. We can extend this to a basis b of Rn, whose first k elements are eigenvectors of A corresponding to the eigenvalue mu. Okay, and we're going to let P be the matrix whose columns are the elements of this basis B. So the first k elements of P are eigenvectors of A corresponding to the eigenvalue mu. Okay, P inverse AP is a matrix that describes the linear transformation determined by left multiplication by A with respect to the basis B. Okay. When we multiply V1 by A, we just get the scalar multiple mu V1. Its coordinates with respect to B are mu for V1 and 0 for all the others. When we multiply V2 by A, we just get the scalar multiple mu V2. Its coordinates with respect to this basis B are just mu with respect to the second basis element and 0 with respect to all the others, and so on for the first k elements of this basis B. And what that tells us is that the matrix that describes left multiplication by A, that linear transformation, with respect to this basis B, in its first k columns, all it has is a mu in the diagonal position and zeros everywhere else. It can have anything else. It can have anything in the last n minus k columns. We don't know anything about that. But it has just, it's in its first k columns, it has mu in each of the diagonal positions and 0 everywhere else. So it has a diagonal strip of mu, 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 mu in the first k columns, and the other first k columns otherwise are full of zeros. And that tells us, when we look at the determinant of that matrix, or when we look at its characteristic polynomial, rather, its characteristic polynomial is just going to be the characteristic, is the determinant of a matrix that has lambda minus mu, lambda minus mu, lambda minus mu in the first k diagonal positions, zeros elsewhere in the first k columns, and something down in the lower right region and in the right n minus k columns in particular. But that matrix is, in particular, it's a block upper triangular matrix. And so its determinant is the determinant of that upper left k by k diagonal part multiplied by the determinant of the lower right square part that complements that. And in the upper left area, we just have lambda minus mu occurring k times along the diagonal positions. So that's telling us that lambda minus mu, that factor, is occurring k times as a factor of the determinant of lambda times identity minus p inverse AP. So k times, at least, as a factor of the characteristic polynomial of A. Okay, and a corollary of this theorem then is that since every eigenvalue of the matrix has geometric multiplicity at most equal to its algebraic multiplicity, the matrix is diagonalizable if and only if it has a basis consisting of eigenvectors. And that can occur, and does occur, if and only if every eigenvalue has geometric multiplicity which actually is equal to its algebraic multiplicity. So if there are any eigenvalues, as in that example, the 3 by 3 example B that we just looked at, whose geometric multiplicity is strictly less than its algebraic multiplicity, then the matrix just doesn't have enough eigenvectors to have a basis consisting of eigenvectors, and it fails to be diagonalizable. So we knew that a matrix is diagonalizable if and only if it has a basis consisting of eigenvectors. Another way to capture that idea is it's diagonalizable if and only if for every one of its eigenvalues, it has geometric multiplicity equal to its algebraic multiplicity. If there's any eigenvalue for which the geometric multiplicity is less than the algebraic multiplicity, then the matrix is not diagonalizable. And of course, if all eigenvalues occur with algebraic multiplicity 1, which is the case where the matrix has n distinct eigenvalues, then as we already know, the geometric multiplicities will all have to be equal to 1 as well. And the matrix in that case is diagonalizable. Okay, that's it for chapter 3, and that's it for this lecture. And that concludes our work on chapter 3. We're going to continue next time with a look at inner product spaces. So thank you, everybody, and see you next time.